exponential functions. In this video, we're going to look at some of the properties of exponential functions so that we can make sure we understand how to apply and use them in the context of various things we'll look at in this class. This is going to be in direct comparison to what we already know about polynomials and linear functions and how those are structured. So this is going to focus here on exponentials. So an exponential function has the form y equals k times a to the x. The key thing here is that our independent variable is up in the power. When we're talking about polynomials or linear functions, our variable is down in the base. But with exponential functions, our independent variable's in the power. Note here that k and a are both constants. Some examples of exponential functions are listed here. Y equals 5 times 6 to the x, y equals 2 times 1.4 to the t, so on and so forth. You will notice that this example here has an e in it. That is something that we use a lot. E is a number, just like pi is a number, and it comes up a lot in nature and biology, so we use it quite often to model things. So whenever you see the variable up in the power, that should be sort of a signal to you that we are dealing with an exponential function. So example 1. For each of the following exponential functions, compute the value for t equals 3. So here we just want to get comfortable being able to plug these things into our calculator and to write them out to compute them correctly. So for this first one here, we're going to do 2 times 3. Now t is our power, and we're plugging in 3. So 2 times 3 cubed. So 3 cubed is 27. 27 times 2 is going to give us 54. Now, I don't expect you at all to do these in your head. These are things that you can plug into your calculator, especially with the decimals and as the numbers get bigger. So for our next one, we have 0.5 times 1.2 cubed. So we do have order of operations here. So you want to cube the 1.2 first and then multiply by 0.5. And when I do that, I get 0.864. So hopefully you are getting the same values as you try plugging in the 3 everywhere. For the next one, we have 25 times 0.35 cubed. When I plug that in, I get 1.072, we'll call it. I rounded both part B and C to 3 decimals. It didn't explicitly say what to round to here, but you should be getting the same values. And then finally for part D, we have 2 times e to the t. So we have 2 times e cubed. So there should be an e button on your calculator. It usually will say e to the x, and x is what we're plugging in. That's what you're going to want to be using. So when we plug that in, we are going to get a value of 40.171. So as we look at these, this first step again is just getting comfortable plugging things in and recognizing that we are working with exponential functions. So let's talk about why we want to use exponential functions and how they're going to help us on our journey in calculus. So one of the main reasons that we're going to be looking at exponential functions is to represent growth and decay, and this especially comes up in the natural sciences. Things like carbon dating, if you've heard of half-life, that is exponential decay. When we talk about population growth for anything from animals to plants to bacteria, all of those things tend to follow an exponential growth pattern. So these exponential functions come up quite a bit in the sciences. And so the general form that we talk about when we're talking about growth and decay is P equals P naught A to the t. So oftentimes when we are modeling something in biology, chemistry, microbiology, anything of that sort, we're looking at what happens over time. So instead of using the x, which is sort of a conventional independent variable, we'll often use t because we're talking about time. And p here is because we're usually talking about a population and how it changes. So p sub 0 or p naught, this first sort of thing that we see here, this is going to represent our initial population. This is a constant. This is not the variable here. This represents the amount that we start with that we're modeling over time. T is time. So if a problem says the time is in minutes, then time is in minutes. If it's in hours, it's in hours. But T represents time. And then we have this factor A. And A is 1 plus R, where R is going to be the rate at which you are changing. So what that means for us is that if we are growing, right, then R is going to be positive. And if we are decaying, then our rate is going to be negative. So it really depends on the situation, and we'll look at some examples in a few minutes that we look at both cases. So it's really important here to remember that T is our independent variable, that P naught and A are going to be constants here, and A is going to be a positive number. So A is 1 plus R, and so I want you to imagine if something was decaying 100%. If we turned that into a number, that would be -1. So we can't really decay more than 100%, so it doesn't make sense for A to ever be negative. So as I said before, P naught is going to represent the initial value of our function. So we talked about what R means in terms of growth and decay, but we can also now situate that with A, since A is 1 plus R. So if A is greater than 1, that meant that R was positive and we have growth. And if A is between 0 and 1, that means we have exponential decay. So again, I really want to compare this to linear functions. So linear functions have a constant rate of change. So when we talk about y equals mx plus b, right, that m is our constant rate of change. So it's always changing by 4 units or 10 units, whereas exponential functions are changing by a percentage and not a nominal amount. So that's one of the major differences between linear and exponential functions. So let's look at an example so we can sort of compare some different exponential functions. Example 2. Suppose that 4 functions below each represent the population in thousands of a different town and how its population changes over time t in years since 2010. So we have 4 towns, town 1, town 2, town 3, and town 4, with different initial populations and different growth rates. And we have 4 questions that we want to answer about these towns. So part A, which town has the largest percent growth rate? So when we're comparing growth rates, it's important to recognize that the largest, we're going to be looking for the biggest number in the positive direction. So if you think about it as a number line, which one is the farthest to the right? So large positive numbers are always greater than negative numbers. So for each of these, let's see if we can figure out what the rate is going to be. So remember, I'm going to put this up over here. A is 1 plus R, and we are trying to find the R. So we're looking at what's in the parentheses here. So here, if I subtract 1 from 1.37, I get my rate here is 0.37. If I wanted to write that as a percentage, I could write it as 37%. But for now, I'm going to leave it as a decimal. For the second one, I have 0.68. So notice that this is less than 1. So in order to get my R, I need to subtract 1 from 0.68. So 0.68 minus 1 is going to give me a negative number. So here, my R is negative 0.32. So the negative is important because the negative tells me that my population is declining in the second one here. For number 3, same idea. We have to subtract 1 from 0.35. Since 0.35 is less than 1, we're going to get a negative rate here. So I get negative 0.65. And then for my last population here, I have 1.28. If I subtract a 1 from that, I get 0.28. So if I'm looking for the largest percent growth rate, since I have some that are negative and some that are positive, I'm going to look at my positive rates and determine which one's the largest. So my 0.37 is the largest rate of these towns, so that's going to be town number 1. Part B, which town has the largest initial population? So remember, when we set up a population model, the initial population is the number that is in front of our A factor. So those are the numbers we're comparing. So we have 250, 1200, 125, and 500. So clearly here 1200 is the biggest number of those four. So that is going to be the largest initial population. So town 2 starts off with the most amount of people. Part C says which town has the largest population in 2015. So remember, in the setup of our problem, we said T is in years since 2010. So time equals 0 is 2010. If we're interested in what's happening in 2015, we're really asking which population is the biggest when T equals 5. So we need to take a 5 and plug that into each of our models. So for number 1, we'll do 250 times 1.37 to the 5th. So I'm going to write this over here. So our population for town 1, when we plug in a 5, is 1206.54. I'm rounding to 2 decimals here, mostly because I think that will be enough for our comparison to figure out which one's biggest. For town 2, when we plug in a 5, we have 1200 times 0.68 to the 5th. So that's going to give me 174.47. Remember that the population is in thousands. So even though we have decimals and that feels a little weird for fractions of people in a town, this is in thousands. So population 3, if we plug in a 5, 125 times 0.35 to the t, my population is going to be 0.66 thousand. And then last but not least, population 4, we have 500 times 1.28 to the 5th. When I plug that in, that population is 1,717.98. So it turns out that the population of town 4 is going to be the biggest. So we knew that 1 and 4 were growing, so they had potential, but we also knew that town 2 started with 1,200, so it depends on how quickly that decays versus how quickly the other things grow. So we ended up with 4 here. Part D, which towns are growing and which towns are decreasing in population. So again, we're going to be growing if our rate is positive or if our A is greater than 1, which was happening in town 1 and town 4. And we're going to be decreasing in population if your R is negative or subsequently your A is less than 1 but greater than 0, which happened in towns 2 and 3. So let's take a look at another example. The amount of adrenaline in a body can change rapidly. Suppose the initial amount is 15 milligrams. Find a formula for A, the amount in milligrams, at a time t minutes later if A is increasing by 0.4 milligrams per minute or decreasing by 3% per minute. So we're setting up 2 models here, and the key part of this question is to figure out how we interpret information, and so how we decide how we're going to set things up. So there's 2 important factors in each of these statements. First is whether we are increasing or decreasing, because that will impact our model. Is something getting bigger over time or smaller? The second is how the change is reported. In part A, we're increasing by a set amount. So for every 1 minute that goes by, we increase by 0.4 milligrams. Another minute goes by, another 0.4 milligrams. Another minute goes by, another 0.4 milligrams. So it's always the same rate, which means that we have this constant rate, and this represents a linear function. So here, our function, we're starting with 15 milligrams, and then we're adding 0.4 milligrams every minute, so times t. So if 10 minutes has gone by, we would have 15 plus 4, we would have 19 milligrams of adrenaline. So the way that this information is reported is as a set amount, and that's what tells me that I should set this up as a linear function. For part B, I can see that we're talking about changing by a percentage, right? And so when you see the percentage, that's what should tell you that we're talking about an exponential function. So a couple things here. We're still starting with the 15 milligrams, so that's going to multiply our A. And we know that we have a number raised to the T. So that number is really important. We're decreasing by 3%. So my R here is 0.03, but since I am decreasing by 3%, that means my R is negative 0.03. So my A, which is 1 plus R, is actually going to be 0.97, because since I'm decreasing, I have to take that 3% away. So I have 15 times 0.97 to the T. So this is the power of T. It's not times T, it's up in the power. So that's the difference between the two models based on the type of information that we're given. Let's try one on a graph. Example 4. A deer population is growing exponentially and the graph of a function is given below. Find an exponential model for the following graph. So you'll notice here that unlike a linear function, this function has a bend to it. So when you have an exponential function, it's curved either upward or downward. It could be increasing or it could be decreasing depending on what the population is doing, but it's not a straight line. So that's something visually that we can recognize. Now we have to remember what the form is for an exponential function. So here we're going to have y equals k times a to the t. So remember here, t is our variable. A and k, our initial amount, and our a, which is our factor, are both numbers. So our job is to try to figure out what the k and the a are here in order to figure out our model. So we have two numbers here. So let's start with the 0, 80. So what I want to do is I want to take the dependent value and I want to plug it in over here on the left, the 80 equals k times a to the 0. Remember that anything to the 0 power is going to equal 1, right? So this term here is going to equal 1, and that tells me that k will have to equal 80. So now my model is a little bit better. So I have y equals 80 times a to the t, but I still need to figure out a. So now I come over here and I see I have another data point. I have 6 180. So again, I plug in the dependent value on the left, and then I plug in my independent value of 6 over on the right. And again, we're plugging it in for t because t is our variable. So now I see here I can divide both sides by 80. And when I do that, I'm left with a to the 6th equals 180 over 80. So I take the 6th root of both sides. And there's two ways you can do this. You can use the root button, or you can raise both sides to the 1/6 power. Because if you have a power raised to a power, the powers multiply and they cancel. So 6 times 1/6 is 1. So a is going to equal 180 divided by 80 to the 1/6 power. You can plug that into your calculator and you're going to get that a equals 1.447 approximately. So now I can come up with my final model here, right? I know my starting value was 80. I know my a now, 447 to the t. So again, my goals here were to identify the starting value and the a, and I found the starting value using my first point. I did this first because of the 0. That makes everything a little bit easier when you can plug in a 0. So I chose to go that route. And now I have a model that I can predict the deer population at any time. So if I wanted to know at 5 years, I could plug in a 5, and I would be pretty confident from my graph that it would be somewhere in the 140 to 160 range. But I could predict it for any time. Let's take a look at another example. Example 5. Suppose a new drug is administered to a patient and the amount of drug present in the blood is measured over a 5-hour period with data recorded below. Find a model for this function. Similar to our last graphing problem, I want to use the data in the table as points to try to come up with a model. So the first thing that I want to notice here is that there's 100 unit difference between 0 and 1, and there is a 60 unit difference between 1 and 2. Now these are both negative if we're talking really formally, but the reason I'm checking that real quick is because if the difference is the same down the whole table, then the table is linear, and I can use slope and point to get an equation of a linear function. But here, I see that these are not the same. The difference was 100 and then 60, so I'm going to try an exponential model to make sure that that works. So remember again, the generic form of an exponential model, we have y equals k times a to the t. So again, I'm lucky that I have a t equals 0. If I didn't, I could still do this, but the math would take just a little bit longer with some more algebra. If I carefully plug in my values, I'm going to get 250 equals k times a to the 0. And we know that a to the 0 is 1, so that tells me that k is 250. So now my model becomes y equals 250 times a to the t. If I want to now solve for a, I need another data point. So I'm going to pick the 150. I find that the smaller the t, the easier it is to do the algebra and work with things, but you could choose any other point on this table and you should get the same result. So now I plug in that point, so I get 150 equals 250 times a to the 1. Well, that's helpful. A to the 1 is just a, so I just have to divide both sides by 250. So a is 150 divided by 250, and that's going to give me 0.6. So my a here is 0.6. So now my model is y equals 250 times 0.6 to the t. So what do I notice here? One of the things I notice is that my a is less than 1, right? 0.6. So that indicates to me that this function should be decaying. And if I look at this table, I can see the dependent values going down. 250, 150, 90, 54, 32. So that matches what we know should be happening. Now, if I use 2 points on a table to come up with a model, I always like to pick one other point on the table to make sure that I didn't mess something up along the way. So if you were to take 4 and plug it in for t and check on your calculator, you will see that you do get 32.4. So this feels pretty good, and we found our model for this data.